Hello everyone, we are Team 12 and this is our interim presentation on the analysis and redesign of an optical microscope. The BN107 is a binocular biological microscope designed for lab and educational use, offering a total magnification range of 40 times to 1600 times. These microscopes are used to analyze and view objects not visible to the naked eye, commonly used in the study of cells, tissues, and material microstructures. It is manufactured by multiple companies, including Opto-Edu with 60,000 units per year and FY Microscope with 50,000 units per year, yielding at least 110,000 units manufactured yearly.
The primary customer is professional scientists and researchers who use the microscope daily and require reliable performance, increased magnification, and 2 eyepieces for an easier viewing experience. A secondary customer is educational institutions such as high school and college students. The secondary customer values a low-cost, durable, and easily portable microscope for the classroom. The main function for the microscope in the FAST diagram is to analyze the specimen of interest. The basic functions are to magnify the image and illuminate the specimen. From this, it includes focusing the image with coarse and fine adjustments and selecting the magnification. And then for illuminating, the product needs to generate, transmit, and control the light. The supporting functions are assure dependability, assure convenience, enhance product, and please senses, which are branched out into further functions.
There are 2 proposed assembly sequences shown in the fishbone diagram. The first sequence starts with the lens subassembly. We then move to the eyepiece assembly, followed by the light subassembly. Next comes the stage assembly, and finally the base assembly, where the main body is put together. In the second sequence, we begin with the base subassembly, followed by the focus mechanism assembly. Then we move to the light and lens subassemblies and finish with the stage and eyepiece assemblies. Sequence 1 is preferred over Sequence 2 as it offers better ease of locating parts and allows for parallel subassemblies and testing of subassemblies. This is a function component mapping matrix. A total of 19 subcomponents of the microscope are matched with their corresponding functions.
This is the exploded CAD view of our product. We have 19 unique parts, not including fasteners, and these parts all align with the numbers in our bill of materials on the next slide. This bill of materials shows the materials, manufacturing processes, assembly processes, and cost estimates for each of the 19 parts. The 4 lenses and the light are assumed to be purchased components. The primary materials for the manufactured components are aluminum, low-carbon steel, stainless steel, ABS, and silicone. The manufacturing processes include turning, die casting, injection molding, and sheet metal working. The total cost estimate is $255. This is a reasonable production cost estimate since comparable microscopes are priced around $300 to $400.
Here is a quad chart showing all of the parts in our microscope assembly. On the left side, we have the functional importance, and on the top, we have the manufacturing or assembly costs. Each part is grouped depending on how important and how expensive it is to produce, with our main area of focus going to be the parts that are of high functional importance and high manufacturing costs. Those parts being the microscope body, top stage, and 4 lenses.
Moving into product family design, this is our functional differentiation table. As you can see, the majority of our functions are the same for both our primary and secondary customer groups, and we have 3 that are different. Select primary power and enable stereoscopic viewing are 2 functions that are more relevant to professional researchers and scientists, which is our primary customer group. And then enable portability is a function that we have identified as being relevant to our secondary customer group, which is educational purposes.
This is our component commonality table. The primary variant has 5 modules, while the secondary variant has 4. In the primary, they are 4-prong lens rotator, head, base, dual eyepiece, and lens times 100. In the secondary, they are 3-prong lens rotator, head, base, and singular eyepiece. In order to define our modules, we took a look at the function component mapping matrix, and we can see that the corresponding parts to the functions of enable stereoscopic view, select primary power, enable portability are the head, lens rotator, and base, respectively. Also included in our modules are the eyepiece and lens times 100, which are different for each of the two variants. Shown also are the costs for each module from the bill of materials. As you can see, researchers and scientists will be paying more for stereoscopic view, higher magnifying lens, as well as more control over primary power than the educational users. In this slide, you can see the CAD visualization of the component design for primary users on the left and secondary users on the right. These are the common interfaces between the platform components and each module component that allow plug-in of the modules for the primary product variant. This assembly sequence realizes delayed differentiation. Both variants will have the same subassembly for base, light, and stage. Only at the point of assembling the eyepiece and lens will the subassemblies differ. Compared to the original assembly sequence, the modified sequence has been flipped. There are also two separate variants rather than one.